Everyone, thank you for coming. I'm Steven Spatz, Assistant Outreach Librarian, and on behalf of Library Director Joe Lucia and the staff of Falvey Memorial Library, I'd like to welcome you to a special annual event in our Scholarship at Villanova lecture series, the Outstanding Faculty Research Award Lecture. Supporting the production of original research is central to the mission of Villanova University, and one of the ways in which the exceptional scholarly achievements of our community are recognized is through the annual presentation to one deserving faculty member of the Outstanding Faculty Research Award. Each spring semester, we are proud to host the current recipient of the award as they present their work here in the library. This afternoon, we're pleased to have with us the 2011 Outstanding Faculty Research Award recipient, Dr. Robert Jantzen. Bob Jantzen, professor in the Department of Mathematics and Statistics here at Villanova, is a highly distinguished scholar with over 100 publications to his name on topics in general relativity. He's a dedicated teacher as well, with far-reaching ideas on the importance of active learning in mathematics education. Today he'll treat us to a presentation entitled General Relativity, Cosmology and Pasta, A Life of USA-Italy Academic Commuting, during which he will impart the essence of his research to us, a general audience, through reflections on a favorite aspect of his travels to Italy, and a nod to the influence of Italian mathematicians on the development of general relativity, pasta. I say that things could only be better if we here were made to reflect upon mathematical cosmology within our own steaming plates of cheesy tomato eggplant cavatappi. Would you please welcome 2011 Outstanding Faculty Research Award recipient, Dr. Bob Jantzen.
I hope I live up to the hype that brought you here. I should first say that my second institution is the International Center for Relativistic Astrophysics, which is housed at the Department of Physics at the University of Rome. And in fact, the asterisk refers to the buildings that the physics department occupies. The first one is the Guglielmo Marconi Institute, or building. He was the father of wireless communication, so in fact, maybe we should do something with our devices at this time. That didn't work, I better turn it off. And the second building is named after Enrico Fermi. He was the father of controlled fission. Not so well known are products of Italy that have to do with mathematics and science. In fact, Italy has a well-known tradition in advanced mathematics, and even I, having used these tools for over 40 years, did not really appreciate the importance to which two Italian mathematicians actually played in performing the service for Einstein of giving him the tools that he needed really to develop the general theory of relativity, which is his theory of gravitation. So I thought I would use the Cavatappi pasta, which means I can't ask you if you know what the name of this pasta is. Here's the Cavatappo liscio, the smooth one. Normally they come ridged. I'll show you that in a moment. And on the right, I've got basically the mathematical representation of that surface. And you can see sort of a grid. You take this circle at the bottom, that green circle, then basically you rotate it around the vertical axis, and at the same time you translate it upwards, and that generates this helical surface, which is this Cavatappi pasta, and it has a nice symmetry of this screw rotation. When you screw a metal screw into a piece of metal, you keep turning it, and it always looks the same. The threads look the same because of that symmetry. Symmetry plays, in fact, a big role in physics and in actually getting solutions to the equations of physics, so I'll talk a lot about that eventually. Let me go back to my dedication here. This weekend, we were fortunate to go to the memorial service for Fang Li. Fang Li was a relativistic astrophysicist who was not only a brilliant guy, but stood up for his belief that we all have the right to speak truth to power, and he was, in fact, one of the democracy movement leaders before Tiananmen Square. Spent 13 months in the American Embassy with his wife. I'm not sure how she could stay in a room with a physicist that long, but she survived. And unfortunately, he left us too soon, but we'll remember him. If we go over to this other page, you can see a brief click and see some images of Fang Li. He was associated with our group in Rome and was a true friend of not only my professor Remo Ruffini there, but also of Ani and I. And that reminds me of another thing. If this were a game show, my in-laws' favorite TV show is Wheel of Fortune with Pat Sajak and Vanna White. And when they interview the contestants at the beginning, they say, oh, and I'm here with, joined in the audience by my lovely wife and life partner, Ani. Could you stand up, Ani? Yeah. So let's get to the talk. I'm using Maple 16 as my presentation device. Everybody else uses PowerPoint, but for mathematics, this enables me to actually engage in the mathematics as I'm presenting it. Mostly, I want to do the graphics to give you some clue about the ideas of the mathematics that underlie some of the work that I've been doing over the years. Let's first take care of the mathematical formulas of that surface. You saw some grid lines there. They're circles that correspond to those circles that are being rotated. And then there are these flow lines that go along the Cavatappi. Those are the symmetry lines where you take the points and sort of, they're the paths that as you rotate them around and translate them up. So this has that symmetry of the screw rotation symmetry. And we need mathematical formulas to describe those. I have to thank Tim Feeman, where are you, Tim, for calling my attention to a book written by a crazy architect in England who found mathematical representations for 90 different pasta shapes and published them in a book. Optimal design. I'm going to pass this around so you can look at them in case you get bored. I also brought another prop. Pasta goes by many names in Italy. They can't seem to agree ever. If you go to Whole Foods, you'll get the whole wheat version, which we prefer for its nutritional impact. These are called gobetti. Maybe you could tell me a little hunchback or something. What is it? Hunchback.
It means hunchback.
Pasta tarong. So there's some equations, and some particular values of the parameters enable us with these two free variables. You have a u and a v parameter, and as you vary both of them, then the image of this in free space sort of sweeps out that Cavatappi surface. One of the two variables goes around the circle, and the other one goes along those parallels. And of course, we can then study their geodesics. I'll talk about what geodesics are later. Here's the Cavatappo rigato as ridges. So instead of having just a circle, we put a little bit of a wrinkle around the circle in order to make those ridges. And I've shown what I've called the outer equator in red and the inner equator on green. There's like the outer equator, which is the equator on the sphere. We'll see that in a moment. And because it's got a second side, it's got an analogous inner equator. In fact, you could think of this as taking a donut, which has an inner equator and an outer equator, cutting it down and then opening it up and twisting it up, just like you see in this picture. That would form one revolution of this Cavatappo. So what are the geodesics? Well, I'll talk about geodesics in a moment, but they're paths that go along the surface, which locally are the shortest distance between 2 points, but are globally defined more appropriate by the fact that if you think of yourself as a little car going along the surface, you lock your steering wheel straight forward and keep on going always forward, and you will follow that self-parallel path, which is called a geodesic. And I'll show you a film of that in a moment. So we have these two variables. In this case, I've called them r for going around the circle, a radial variable. And there's another coordinate theta, which is the angle around the axis. So we need equations for how you move along these curves. It's like motion from a force in ordinary 3 space. Newton's laws say the acceleration is equal to the force divided by the mass. So here we have the acceleration, second derivative of one of the coordinates. And then there's a very long expression for the non-smooth Cavatappi. It only depends on r, though, because of that symmetry. The angle theta doesn't appear.
I saw a mistake there.
And I'm showing this only for one reason. It's easy to do these things numerically, but you need a computer algebra system really to develop the equations and to then be able to solve them. This is not something you can do by pen and paper like in the old days. In fact, the beauty of present-day mathematical education is that we have these tools that enable us to do so much more than just pen and paper and to engage in the mathematics and see really interesting extensions of what the simple ideas that we do in our toy examples for homework have to do with. Okay, so let's go beyond this. I just have to go a little bit into the history before I try to look at the ideas. So let me...
So R of t goes in for u and theta?
R of t is the distance from the outer equator around the circle. Mm-hmm. So if I had a unit radius, it would actually be the angle going from minus pi to pi in order to go around that circle. Mm-hmm. So who are the names in the history of this? In the 1800s and early 1900s, the center of mathematics and science was in Germany, whatever it was called at the time, at Göttingen. which I'm mispronouncing probably. Gauss was a giant mathematician in the sense of mental prowess. He was the first to really develop the ideas of the geometry of a two-surface and the ideas of metric and curvature in a two-surface. And his student, Riemann, then extended the idea to n-dimensional curved spaces. N-dimensional, But he died too soon, really, to do more with it. In turn, there was an Italian, Ricci Corbastro, who then took up the idea, and he developed the tools of so-called tensor calculus, which is the prime mathematics that one needs to describe curved spaces, and made incredible contributions to differential geometry. His student, Levi-Civita, worked with him together, and in 1900 they published a book, a very long paper summarizing all their methods in French, unfortunately. So at the same time, there was another Italian mathematician, Bianchi, who did a lot of work on symmetric spaces, and we're talking about symmetry here, so he plays a role. In fact, his spaces, which talk about how three-dimensional spaces can be curved, but yet still homogeneous, we'll talk about that later, later became used by physicists as cosmological models, and I'll try to get that at towards the end of the talk. How do I fit into this? Well, Grossman was a friend of Einstein, a mathematician, and Einstein was not really good at mathematics, but he took this paper from Ricci and Levi-Civita and taught Einstein how to use these tools while he was trying to come up with this theory of general relativity, and eventually in 1916 he did publish the final theory. Fermi at the time was a high school student, and then just a couple of years later a graduate student in Pisa, which is where these other Italian guys had been, and he did some of his first work in general relativity, which I had the privilege of helping translate recently, and I translated a couple articles of Levi-Civita as well. But just to move on, Einstein was once asked about what he liked best about Italy, and his short reply was spaghetti and Levi-Civita. In fact, Levi-Civita helped him along the way through correspondence to help guide him in using his tools properly to come up with this theory. In fact, Fermi and Levi-Civita were both victims of the fascism in the 30s. Levi-Civita was removed from his post and sort of broke him. He was older, though. Fermi was a young guy. He came to the United States, where, in fact, he did the research on nuclear fission. At Princeton, which is why I mentioned Princeton there, a lot of these immigrants fled to Princeton initially. There was Robertson, who was my academic grandfather. He was the Ph.D. advisor of my advisor, A. Chow. Robertson was one who developed a lot of the mathematics of the most symmetric cosmological models that people hear of when they talk about popular expanding universes. Taub was a student at Princeton under him, and he was in fact the first one to systematically use these Bianchi cosmological models to investigate their dynamics. After Einstein's friend Gödel, who had an interest in rotating cosmologies all his life, actually used a couple of those models to introduce his crazy Gödel solution, which had closed time-like lines and sort of was very upsetting to the physics community at the time. Also figuring in this is Amy Noether, who was a couple of years over here at Bryn Mawr. She was a brilliant mathematician in Europe, but she couldn't get a real job there, so she had to come to the United States to have a position. And her contribution was to understand how symmetry of systems leads to conserved quantities that help us understand better how the solutions to those systems behave. We're all familiar with conservation of linear and angular momentum. If you're a skater and you're going around and you're bringing your arms because of the rotational symmetry, conservation of angular momentum makes you go faster. So it's a really important principle in physics, and in fact in our problem with the Cavatappi pasta. So that's the historical section. Let's come over to the geodesics that we have to learn about. So I guess this is me in my office. I like to sketch. So there's a lot of fine print here and some mathematics that we're going to just jump through. Really want to show you the pictures. So we'll start with trying to understand geodesics, beginning with, open up guy, the flat plane, which we can think of as having a grid of constant values of our two coordinates that we use to describe points and position in the plane. And of course we know that the straight lines have a privileged position in the flat geometry of the plane. They're the shortest distance between 2 points, and they're also autoparallel in the sense as we move along them, the direction doesn't go left to right. It always stays straight. straight lines we need to generalize to curved spaces, and we'll call them geodesics. How do we control the geometry? Well, we can use different kinds of coordinate systems to represent our points in our space. Here is a coordinate grid associated with polar coordinates, the angle around the center and also the distance outward from the center. And if we take that same straight line and we zoom in on it, you can see that the grid here, the more and more you zoom in on it, and the finer that you make the grid, those little grid boxes look just like rectangles. And in fact, we know the geometry of rectangles well. In fact, that's the basic idea of calculus. You take a curve and you zoom in on it. Let's go to my manipulator to scale. What's going on here? There we go. Why is it not behaving right? Well, I wanted to zoom in.
Because you wanted to.
Now it's doing a dual function for the. Well, if you zoom in, you'll have to imagine it. The closer and closer you get to there, the more and more this is going to look like just a piece of a straight line. And then it has a slope. We all know about slope from high school. That's what the derivative is. So in fact, this idea of zooming in is really the key tool of all of calculus. And we can use it for understanding geometry of surfaces as well. So if you have a basic rectangle, we need to know how to compute lengths. And from lengths, if we know all the sides of a triangle, we can compute angles and things. So how do we compute lengths? Pythagorean theorem. We all know that from our infancy. If you have two lengths of a side of a triangle, I'm going to call them dx and dy for differential elements of our two coordinates, x and y. Then we need to know what's the hypotenuse length, right? A squared plus b squared is c squared. So what we call the hypotenuse the differential of arc length, s, just the distance symbol. So we get this formula that the square of the hypotenuse is the sum of the squares of the sides. That's the Pythagorean theorem, but in this differential context of a small grid box in our grid. So in fact, if we take one of these grid boxes from our polar coordinate system, and if we zoom in far enough, it's just a rectangle. So we need to be able to figure out what the length is to go across the rectangle. If we go in the radial direction outward from the origin, it's just the increment in the radial coordinate. But the angular coordinate doesn't directly measure length. We have to multiply by the turning arc, because angle times radius of turning arc gives you distance along the arc. So we have to multiply by this scale factor r, which is the actual value of the radius. And we take Pythagorean theorem, we get what is called the metric expressed in polar coordinates. It's the s squared is the r squared plus r squared d theta squared. That's basic multivariable calculus stuff. So, well, we can also handle parallelograms. Not all coordinate grids have rectangular boxes. They can also have parallelogram boxes if we sort of zoom in on them. So we need to then look at the geometry of parallelograms. And if you remember back in high school, when you have a parallelogram and look at the main diagonal, you've got a triangle on either side. How do we compute the length of the third side of the triangle? Anybody remember? Law of cosine, thank you. Law of cosine. So yes, in fact, there's an extra term in the Pythagorean theorem, which is got extra stuff in there that makes it a little bit uglier. So in fact, we get a little bit more complicated formula for the arc length, which is determining our geometry, if those grid boxes are not perpendicular. In fact, in general, we would have an expression where we have the Pythagorean contribution scaled by the appropriate things that make the arc length out of the coordinates, whatever they are, plus something that has to do with the angle in between for the parallelograms. And that's our basic tool for geometry. Well, suppose we look at a cylinder. Cylinder is still flat. Well, it's intrinsically flat. If we cut it along the blue line and open it up, it's just flat. It's just the plane that we were dealing with. And of course, the straight lines in the original plane are the straight lines, the geodesics, on the cylinder if we just wrap it back up. So there's that straight line from before in the plane, but now it's wrapping around the cylinder because it's extrinsically curved, even though it's intrinsically flat. Okay? We're interested in the intrinsic geometry, not the extrinsic geometry. So let's go on to a space that's really curved. That's the sphere. We're all familiar with the sphere. People needed this geometry of the sphere because of navigation in the old days, even before they cared about differential geometry. And we all know that the sphere has what? Lines of latitude and longitude. The longitude lines are exactly great circles, as is the equator. But in fact, if you fly from New York to Europe, you know on the map that you see on the plane, it looks like we're going up and coming down, because the rectangular map doesn't quite fit the fact that it's actually a great circle going in the shortest distance between the 2 points. These great circles can have any orientation, and they're formed simply by cutting the sphere with a plane that goes through the center. So there's a plane that goes through the center. There's the intersection, it's a circle, and there it is put back on to the sphere. So we get a great circle on our sphere, and we can zoom in on it. I'm not going to risk my mouse not working, so I did this in advance. And you can see on the sphere we've got rectangular gray boxes, if we're looking at one in the center, for example. So on the sphere we need to know how to convert the 2 angles of longitude and latitude into actual distances. And so there are going to be some correction factors that have to do with the radii of the arcs. So on the sphere we get this sum of the squares because it's orthogonal perpendicular, which gives us the geometry of the sphere in terms of the radius from the pole, the radius r of the sphere, and the 2 angles theta and phi that describe latitude and longitude. Now, in fact, this idea of a geodesic is really fun. I have this in a background. Let's see, where is it? There's a New York Times article that talks about geodesics. There's the route from New York to Europe. In fact, it looks like it's going to Italy. What a coincidence. Well, maybe it's going to Greece. No, it's Italy. It's Italy. Yeah, no. Well, I want to show you this video of a geodesic on a surface that doesn't have symmetry except for some reflections. Here's a double torus. It doesn't have any continuous symmetry, rotation, or anything like that. But I want to show you the geodesic idea of self-parallel paths. It's just a 1-minute video. Even got a soundtrack. Takes a little bit of time to get going. So this shows a motorcycle going along a geodesic highway on that surface. Of course, it's a little bitty motorcycle. Or a bike. Not clear. Motorbike. And that black path is a geodesic. You can see it's not turning left or right. It's always going straight ahead. And this is really the contribution that Relativity gave to differential geometry after the birth of general relativity. He taught this idea that geodesics are not just locally shortest distances, but really the autoparallel curves, and talked about the idea of parallel transport of vectors. And I think that's going to finish in just a moment. Okay, so we'll come back. So this curvature, in fact, this idea of parallel transport, if we take a vector that's not pointing straight ahead, but always keep its angle fixed with our motorcycle, that's the idea of parallel transport. We keep it always parallel as we're going along our path. So if we start on the path, point A, keep something pointing to the north all the way on the equator, and then follow a line of longitude up to the North Pole, and then come back down along another line of latitude, we see that the vector is rotated. That doesn't happen on a flat geometry. When you go around a closed curve, in a flat geometry, we have a global parallelism, and it doesn't matter. But on a truly curved surface, you get a little rotation. In fact, that's how you can measure curvature. You go around a small loop, zooming in with the calculus idea, and you can calculate how much rotation you get for a small little area of the loop. And that's the so-called Riemann curvature tensor. So, in fact, the different kinds of curvature have to do with geodesic triangles. If we take 3 great circles on the sphere, we make a geodesic triangle, and you can see, obviously, the angles are bigger than 180 degrees, which is what happens in the flat geometry of the plane, 180 degrees. If we're on a negative curvature surface, like a saddle, where the sort of circular arcs go in different directions at any point, up here and over, so the circles are on opposite sides of sort of the local tangent plane, if you zoom in on it, that's negative curvature, and on such a surface, the sum of the angles is less than 180 degrees. So very easily measured in terms of local geometry. So what has it got to do with Cavatappi? Okay, there's a famous movie from 1954, 2 years after I was born, called Alberto Sordi. Unfortunately, there's no time to go into that. Here's my own version at the right from the late 1990s. So we have these smooth and ridged Cavatappi, and I already sort of showed this before. We take this, either a circle, or we put a little oscillation on it, we rotate it around the axis, that would give us a torus. But if at the same time we move vertically, we get this spiral surface. And I'm measuring my distance r from the outer equator in both directions, so it's negative going below, positive going above. But it's obviously symmetric going around that object. Doesn't matter whether r is positive or negative. So we have the screw rotation symmetry of the resulting Cavatappi. Here's the smooth one, and you can see the red outer equator. Let's start down at the bottom. And the green inner equator. I can rotate this around very nicely. You can see, in fact, that if we follow the red line, it's always going straight ahead. It is a geodesic, just like the green one. So in fact, those special outer and inner equators on this surface, like the equator of the sphere itself, are geodesics. They're autoparallel. The actual Cavatappi has got the ridges, but let me zoom in a little bit to give you the idea of the grid. Remember, it's the grid really tells us how to do the local geometry. And if I could put a few more lines parallel the angular coordinate, you would see that these are just little rectangular grid boxes. So as long as we know how to calculate the length and the angle, we can then describe the geometry of the Cavatappi surface. Here's the ridged Cavatappi within the inner and outer geodesics as well. And it's kind of cute. Again, we can sort of rotate it around. You can see as I rotate it, it's always, yeah, too much, going a little too fast. This is 20 megabytes. It's the biggest file I've ever made. So I have to be a little bit slow with my mouse. So there are a lot of equations that you need to visualize this stuff. What about the geodesics? Let me just flash them at you again. I've already shown you them. So I have to go through some defining of the E, F, and G, those three functions, and then I have to go through some other stuff, and I make some routines, and then finally at the end we get that Cavatappi. But it allows us to actually calculate the geodesic from any point from the initial circle. So what I can do is I can start out at this prime meridian, that's the black line, where it intersects the outer equator, and I can just choose my angle for where I want to go. And then my routine will simply calculate the path that it will follow. And here's a particular geodesic. If I try to rotate, I'll have to look here to do that. You can see that it's trying to remain always going straight ahead on the curved surface. So even in spite of the bumps, it's always going straight ahead. But of course, in the end, it's winding around this surface.
Do you have this in closed form now, or is it numerical?
It's numerical, of course.
Numerical.
No, you saw those equations. There's no way to do that.
Mm-hmm.
Yeah. So that was just some of the details. Wanted to make this transparent to show you, in fact, another feature. So let me click on this and see if I can right-click and make my transparency set. Take it away. You can see the spiral, and if I look on it on end, of course, in fact, it's just going around a circle. All right, so the helix is a spiral, and in fact, my path is sort of oscillating around my red curve. In fact, we'll see it, the analogy with, say, the Earth-Moon system going around the Sun. The Sun is at the center of the helix. We'll see why it goes up at the same time later. But in fact, the Earth and Moon themselves are rotating around each other, so they're sort of oscillating a little bit about their center of mass as that spirals around the Sun. We'll keep that in memory as we go on and look at how this relates to space-time. Here's that curve again with the transparent surface. Kind of cute. In fact, you can turn it on end, you get a nice pattern. Okay, so fun stuff, but let's move on. Okay, space-time. The brilliant idea of Einstein, you know, he couldn't get a job. He had trouble with the standard route of, you know, graduate school and then teaching. Somehow he got derailed, ended up in the patent office where he was looking at a lot of patents. At the time, there were a lot of them that had to do with timekeeping devices. So he thought a lot about time, and that's what led to his special theory of relativity, understanding how to join space and time. How can we do it here with a quick few animations? Let's consider one-dimensional motion along the x-axis and the xy plane. Here's the little animation. There's the point moving along the path. Done. Okay, so that's in space. But, in fact, we can also include the graph where we include time in the vertical direction to see how it's moving not only in space but at time at the same time, because time is elapsing along the curve. So we put the time axis there, and then we repeat the video. And now it's going to go along a line because it's moving in time at the same time that it's moving in space. So in fact, we join time to the space. Time is clearly different from space, so we have to distinguish it clearly in some way. But we can then visualize the motion in this two-dimensional space-time for one-dimensional motion. So it's an event history of both time and position. Okay, so let's do this. Looks like the sun and the Earth rotating in a circular orbit around the sun. It's not exactly circular, but let's just pretend it is. We can keep it going. Let's just turn this to continuous. Okay, so that makes us happy because we don't want the Earth to stop. The terrible braking experience. So it's going around in space, a two-dimensional space in this case, but at the same time, time is elapsing. So we really need to think, if we want to see the whole motion in terms of events with both space and time tags, we need to go to the space-time diagram. So we need to add time in the third direction, in the vertical direction. And there's the same system, except now at the same time, let's start over. The sun is just sitting still in the center while the Earth is rotating around, but they're both moving in time. So the real orbit of the Earth around the sun is this helix in space-time. Helix, just like our Cavatappi pasta, the orbits are helices, or the outer and inner geodesics, for example. So the analogy is the three-dimensional space-time here is very much like the Cavatappi pasta motion in the surface within 3 dimensions. So let's get back to Einstein and Newton. Of course, Newton invented calculus in order to really describe the basic ideas of theoretical physics, and that's why Newton is such a big name in history of science. He said, well, the Earth in this picture is falling towards the sun. We turn this back on end. As it's rotating around, it's falling inward towards the sun, but it's also got this angular momentum that keeps it going around the sun because of conservation of angular momentum. So as it's falling towards the sun, it's also moving, and so falling and moving at the same time brings it into a circular orbit. That was Newton who says you've got forces that are responsible for doing this. But Einstein said no. Instead, what happens is that the presence of the sun curves the space-time in the space-time diagram near the presence of a big mass like the sun in such a way that the small Earth is trying to go in a straight line in space-time, but it senses this curvature that's forcing a little bit at edge, and it's really an elongated helix in space-time. It keeps going straight, but just a little bit over, just a little bit over, and eventually it comes around and forms a helix in space-time because of that small curvature. And in fact, typical diagrams that you see of space curvature, and now Cole, it's your moment to stand up and show everybody a typical space curvature. These kind of things, really they show just a space section and try to give you an intuition about the curvature of the space alone. So for the presence of a black hole or sun, you've got a picture like this. And in fact, the deflection of starlight by such a curvature of the space makes sense because if you've got a layer of light that's sort of going along, trying to follow a straight line in the geometry, it's going to move a little bit because of the curvature of this curved space. So when you actually look at it, you see it coming from a different position than the one it actually came from because we just looked straight along the line in which the ray comes. So in fact, gravitational field acts like a gravitational lens, and that's another way in which we can actually see dark matter in the universe through the geometry of space-time that's not directly visible, but indirectly visible through this technique. That was my rendition of never trust a black hole. So falling into the space geometry there. Then special relativity, in a nutshell, everything is relative, right? So who's the lunch there? I don't know. I think somebody should tell the rabbit, though, that things are not equal there. So, well, Pythagorean theorem, dx squared plus dy squared is ds squared, becomes, in the geometry of space-time, we have to put a minus sign in front of the time relative to the space coordinates in order to make a distinguishing between time and space, which really are on different footing. And in fact, that allows, if dx equals dt, zero distance along the hypotenuse in space-time. In fact, when dx equals dt, that means that the ratio of dx dt, that's what we call speed, change in distance over change in time, speed. Well, in these units, that's where the speed of light is 1. 0 distance traveled corresponds to speed of light. In fact, light rays join points in space-time that have 0 distance between them. And so there's an inside and an outside, there's some light cone, there's all kinds of stuff to tell you about causality, but really the basic structure of special relativity, which is flat space-time, comes from this difference between trigonometry, Pythagorean theorem, and hyperbolic geometry, which instead of being based on the unit circle, is based on the unit hyperbola. That's a section that is always skipped in the calculus books, but in fact it's really the basis for all special relativity and transformation of speeds that make the velocity of light always 1 in any reference frame, etc. Okay, so what about cosmology? That's general relativity. Let's check the time. How am I doing for time, guys? Never enough of that, right? So let me see. I have some words here. Maybe I should read them myself. Yes. Simplest cosmological models, which are the Friedman, Robertson, Walker, Lemaitre. Lemaitre was a Jesuit, by the way, are either a flat 3-space or a isotropically positive curvature 3-space, which is just a 3-sphere within 4-space, which expands in time. Or there's a hyperbolic analog that is a negative curvature space. These 3 kinds of curvature lead to the simplest cosmological models associated with these 4 gentlemen. And they have maximum symmetry in the sense that any point and any other point can be sort of moved into each other by symmetry transformation. Every point looks really the same as any other point, but the directions at any given point are also the same because of the isotropy of directions. They're fully symmetric in every possible way, just like flat geometry. We can relax the idea of isotropy of directions, and then we get these so-called Bianchi models. They're a whole classification of 3-dimensional curved geometries where we retain the homogeneity, but we allow at each point things to look differently for anisotropy because, in fact, in the universe we can have different rates of expansion in different directions. So let's get into that, expansion of the universe. So we got a sort of length scale that sets the scale for separations between, say, galaxies. And here's, on the time axis, billions of years, here's the radius of the universe, or the scale factor that determines the scales at which which galaxies are separated. The closed universe starts out and gets the maximum length scale and it closes back into itself, a big crunch and a big bang. Then we've got sort of the marginally bound universe, which is spatially flat, expands out before the big bang, always expanding. And then we've got these accelerated models, which led to a Nobel Prize recently, where in fact it's accelerating. Particles in the universe are actually accelerating from each other as time goes on. So these are sort of like space-time diagrams, except the time is in the horizontal direction. In fact, for these more general models, these Bianchi cosmological models that I spend a lot of time working with, we need 3 independent scale factors, 1 for each of the 3 independent directions, because the expansion can be different in different directions, anisotropic expansion. So we have a space of 3 variables, and Einstein equations for these 3 variables, they're only functions of time because of the homogeneity. Any point in space is as good as any other one, so we really only need to pick 1 point and follow what happens in time. So the entire history of the universe for anisotropic expansion would be hidden in these 3 functions. In fact, the simplest case would just be a flat 3 space where the points are expanding from each other, but at different rates in different directions. So I've got a couple diagrams here. Here's our sphere. It's isotropic, homogeneous, every point's good like another. This is a squash sphere. So in fact, the different axes have different sort of curvature radii. Unfortunately, in 3 dimensions, we can't really show a homogeneous squash 3 sphere, but it works in 4 dimensions. You can take a 3 sphere, and you can squash it in 3 independent directions, so it's still homogeneous, like the sphere itself, but in each direction, things look differently at a given point. So let's look at a cosmological model. So here's the simple Friedman sphere expanding in time. So your scale factor just tells you how the radius increases with time. We could also do that with a flat geometry. Well, here's the curved one. Here's the ellipsoid trying to sort of give the idea of a squashed 3 sphere. Let's play that one. You can see it's actually expanding in different rates of change, so which one is longest switching from one to the other. It's an anisotropic expansion. But the flat plane is the easiest to see. It starts out as a square, and then we let it go in time, and you see it's stretching out because it's expanding in all directions, but twice as fast in the one direction. So the simplest cosmological models which allow anisotropy are these called these Bianchi type 1 flat models. there we just need the three scale factors to describe them. So we're in a space of three variables, a three space. It turns out that that has a geometry of its own, discovered by Brodsky-Witt in the 50s. And the Einstein equations for these three scale factors are just the geodesic equations in this three-dimensional space-time. It turns out there's a preferred time direction in this space of the three scale factors, and the rest of them are spatial in character. And the geodesic equations on that space, the space of the gravitational variables, is just the geodesic equations in that metric. The other Bianchi models are not flat. They have spatial curvature. So in fact, as a function of the three scale factors, you've got different curvatures. And the curvature function itself acts like a potential. We'll talk about that in a moment to tie things up, in which its gradient leads to a force field, which pushes you towards higher positive curvature. So it's not just geodesic motion, but it's deflected from geodesic motion by this extra force field due to spatial curvature in the model. Of course, in general, you don't have perpendicular axes. You can allow the axes actually to have non-trivial angles between them. So then you would need three angles as well as three scale factors. That's six variables altogether. And so your space is six-dimensional, but still has a preferred time direction in the six-dimensional space. The rest is spatial. And the DeWitt metric on that thing is the one thing that governs the dynamics with geodesic equations deflected by this spatial curvature potential.
So even the angles are time dependent?
Yes. So how do we make sense of all this? It comes back to symmetry and naming other. Remember, our only important variable here was this radial variable telling our distance around our circle, or almost circle, that's then spiraled into the actual surface. The parallels along which we actually move this circle are symmetry lines. They don't enter into the actual geometry. It doesn't depend on where you are along the angle, only where you are in reference to the cross-section. So everything really only depends on the radial variable r, and because of the conservation of screw angular momentum, we can actually forget about the angle because we can reduce it to a problem involving only the radial variable. And in that, we can actually reduce the problem simply to looking at a so-called potential energy diagram. So it turns out that the radial speed, if we think of particle motion going along this surface, that would be what? The rate of change of r with respect to t. The sum of the square of that plus this potential that I graphed there is a constant to total energy. In fact, if we think of a particle moving on this surface, because the forces that keep it along the surface always act perpendicular to the surface, it really doesn't change the energy. Force has to move in the direction of motion to change energy. So in fact, if this were a particle moving along that surface, constrained to stay on the surface, the energy would be constant, but so too would be this screw angular momentum. Just like on a sphere or a torus, the angular momentum would be constant, and so we would have a way of reconstructing the angular motion later after we solve the radial motion. So if the total between the total energy, so suppose the energy is 2. When they meet, that means that the difference between the two, the energy in this, is 0. The radial speed has to be 0. The difference between the two is the radial speed. So the radial speed is 0 here, and then gets bigger and bigger and bigger to its maximum, and then it gets smaller and smaller and smaller until it goes to 0 again, and then it comes back. So in fact, you see that there's an oscillation in this potential well that describes going away from the outer equator to a certain point, and then having to return to the outer equator and go in the opposite direction because it's symmetric, and then come back and keep on doing that. In fact, the blue geodesic that I showed you did exactly that. It went a certain distance away, the first one, and then it came back and oscillated around the outer equator. In fact, if you're sitting at the bottom of the potential well, you have exactly that energy that can't do anything, it just sits there. The same thing is true if you're at a peak of the potential, because if your energy is exactly at the peak, you actually sit on the peak, and the difference is 0, so you have no radial speed. You're going to just sit there at that radius, and that will be a geodesic. So in the smooth model, which is the dashed one, the outer equator is just this point, which is pi on either side if you have a unit radius for your circle. That represents an unstable equilibrium, because if you slip a little bit away from it, all of a sudden you want to go all the way to the other end. On the other hand, you can have energy that's even higher than that. So let me just zoom in a little bit more on this, look at a higher version. So there I've shown more of this. This is really periodic, because once you start going around the circle, you keep on going around. So if you have an energy level that's up here, it means that when you come close to the inner equator, you slow down, but you keep on going, and then you speed up as you go past the outer equator, and then you slow down, but you never come to a halt, you keep on going. So you keep going around and around the helical surface. So these are sort of unbound geodesics. In fact, this idea of bound geodesics and unbound geodesics is just like motion of planets and comets around the sun. The bound ones are the ellipses of the planets, but then we have these comets that come in and then go out. Some of them, I guess, are closed, but some of them are actually unbound. They just come in once and go out. Those are hyperbolas. Correct me if I'm not right.
I don't think we have any hyperbolas coming in, but we do have hyperbolas going out if they tangle with Jupiter or Saturn.
Whatever. So anyway, you can see that with this one-dimensional potential here, we're able to actually do something very similar to motion of planets around the sun. What good is this for the most complicated Bianchi models that I spent a lot of time working on? Well, there we have those 6 variables. It turns out that the 3 associated with the angles are related to symmetries that are associated with this underlying homogeneity symmetry, where you can translate in any of 3 directions without changing anything in the underlying spaces. So that induces in the corresponding dynamics symmetries like the rotational symmetry, or the screw rotational symmetry in this Cavatappi pasta, which allows us basically to use the conservation of that angular momentum to eliminate them from the problem and consider a reduced problem with only the 3 scale factors, which is much more manageable. So within 3-dimensional space, we can have this dynamics in terms of these, centrifugal potentials associated with centrifugal force when we think about motion in the circle. It's really the same idea, but in the space of gravitational variables for these more complicated universes that allow us to explore a little bit the idea of the possibility of global anisotropies in our models of the universe. So in a nutshell, I've been working both with the cosmologies in my early part of my career, and then with orbits around black holes in the later part of my career, but the basic ideas are this mathematics that was generated by Ricci and Levi-Civita. Just a couple of the props I brought along. Ricci calculus, written by a German a little bit later than Ricci and Levi-Civita, because in the early days they didn't refer to it as tensor calculus, but Ricci calculus. Book of Universe is a friend of mine, wrote a book on the history of all the different models of universes from the early days of the Greeks to the present, and there's a picture of Luigi Bianchi. I was able to get to some friends in Italy. And here's the book, thanks to Dover book reprints, Levi-Civita's book, published in 1927 in English, on the absolute differential calculus, which is sort of the second name after Ricci calculus. And I guess that's the end of my props and the end of my talk. So if you have any questions, I'd be glad to entertain them. How about that pasta book? Everybody see that?
So Bob.
Yes.
So the Bianchi model, after you get rid of the angles, can you assume that the potential is like 3-dimensional anharmonic potential?
It depends on the particular curvature formulas that come from the different kinds of symmetry. So in fact, there are different kinds of pictures that some have closed contours and others are open, and that determines the ultimate dynamics of those kinds of cosmological models.
I think I missed you there. So what I want to say, if you consider that I have 3-dimensional anisotropic harmonic oscillator, it's like having 3 different forces in different directions.
Right, yes.
Maybe it's silly what I want to say, but can I assume that these 3 scales corresponds in the long run by some strange way to the 3 forces of nature?
No, it's just anisotropic expansion of the geometry, that's all. It has nothing to do with other forces.
Not dynamics.
Yes.
So the geodesics of the Cavatappi and that of the torus, if you project them down, are they the same? I mean, if you view them from along the z-axis, would they be exactly the same, or can you actually tell the curve? Can you tell the screw?
Yeah, they're not the same because the vertical movement distorts the geometry in the surface a bit, and so they're going to be different. On the other hand, you can ask the same question for the torus. I was really interested in the closed geodesics on the torus when they come back to your starting point, and therefore you have a periodic motion on the surface. So it turns out that you can figure out different quantum conditions on the orbit parameters in order to make it closed, and you get very pretty patterns because they repeat. you can do the same thing if you look from the top here. You can look at the ones that have project to closed curves. In fact, that one that I showed you was sort of making almost a closed curve. We've got that nice pattern.
Right. Oh, but they're, I see, okay.
But they're also stretching out.
I see. So there's one that would then cover the whole.
Well, most of them.
Okay.
You have very special conditions in order to come back to the same place in the same direction. You can come back at a different angle, but to come back in the same direction is difficult. Yes?
So are there models where the time isn't infinite, but it just...
Well, in fact, Gödel stunned the mathematics and physics community with his special Bianchi models, where in fact it has closed time-like lines, which means that you go in the future, but because it's a circle in this mathematical model, you come back to your past. And of course that violates causality. It's very bad. It's upset people for a long time. So they were trying to figure out how to enforce a cosmic censorship or something into the Einstein equation so that you can avoid this closed time-like line problem, because it obviously can't be physical. Maybe the students have a question? There are a few. Edward.
So go off of that. Well, if you take the model of the universe where we have the Big Bang and Big Crunch, just by the fact that everything would condense down to one point, couldn't you like argue for periodicity just from that?
Well, why would you expect it to bounce back out? That's sort of an assumption, no? This oscillating universe?
Yeah.
Why would you expect it to bounce back out of when it comes to a point? It's too artificial a mathematical solution. Everything is sort of aligned just right to come exactly to a point. But in the real world, things are not so isotropic. A little bit of distortion would mean that they would miss each other and not come to an exact point. So it's a very special condition to actually collapse to a single point. Too much symmetry. You'd have to have some other physical principle forcing it to a single point. Yes, Mike.
Is this your favorite pasta?
I have too many favorites. But it is whole wheat. We're trying to go more nutritious these days. The whole wheat pasta, the whole grain pasta is.
But I mean
a
the
lot.
shape.
The shape is clearly. You can look in the book. There's some others that have sort of a screw rotation symmetry, but they have borders. They don't close. The thing that's very nice about this surface is that there are no edges. It's just very nice and smooth, so it's very highly symmetric and therefore amenable to very nice mathematical treatment. But clearly you can take any of these irregular pastas and at least before you run into an edge, you can consider the same problem of looking at the geodesics on those surfaces. So the architects, they were able to look at the design of these things, but physicists are able to actually go further and look at the dynamics of motion on the surface. Yes?
Motion on the surface. Can you explain with geodesics why Reed Cavatappi absorb sauce better?
Well, there's a second book that's often shown with this on Amazon called the Geometry of Pasta. And maybe it's not well known, but the different pasta shapes are actually suited to different kinds of sauces in Italy, and they're very particular about matching up the sauces with the pasta. We're not so good at that because it's not in our blood. So we try to fake it in matching them up, but I don't know if we're always successful. But with the Cavatappi, we did there's a cheesy tomato sauce one there that you can see on my website. That's pretty good. Comfort food. It's like macaroni and cheese.
But is it because motion on the surface is different on a ridge surface than a...
Well, what the ridges do is make it sort of oscillate a little bit as it's moving. Right, but you see it still had the same kind of structure going around, so that it doesn't affect too much the global behavior of the curve if you ignore the little oscillations.
What do they do? I mean, it does empirically when it takes that.
Well, the ridges are in terms of that, yeah, these showing.
No, because you have mathematical.
The smooth pasta doesn't retain the sauce as well as the rigate. This is the rigate. Usually you find the ridged one because the sauce will cling to it, but if it's smooth, it's easier to slip off. That's another key feature in matching sauces with pasta.